This is the brief on the fundamental physics of vectorial precession. Okay, so we're going to dive into one really important differential equation. d L dt equals v cross L. Now, this equation, it's basically the mathematical bedrock for describing how a system's spin, that's L, changes over time. Think of things like gyroscopes or even magnetic spins. The geometry packed in here gives us three critical insights. First, that cross product is the absolute key to an incredible kind of stability. You see, because the change in the spin vector is always perpendicular to the spin vector itself, it means the vector can't grow or shrink. So this strictly guarantees that the magnitude of the angular momentum is always conserved. Second, the math proves that two crucial things stay constant over time. We've got the overall size of the spin, like we just said, but also the inner product of v and L. And what this really means physically is that the angle between that external field and the spin vector, it never changes. Not at all. Finally, what all this gets you is this pure, steady motion called precession. The spin vector just smoothly traces out a constant cone as it rotates around that fixed axis, which is defined by v. And maybe the most elegant part? The rate of this precession, often called omega, is constant, and it's determined precisely by the magnitude of that external field, v. This concise differential equation neatly predicts steady, conical rotation purely from the geometric properties of the cross product.